Okay, this is the next question. Here I have taken a simple harmonic motion which is moving under frictional force. So one by one we are moving to advanced sections. In this problem we have friction. So before starting simple harmonic motion theory or simple harmonic motion problem, I want to discuss friction with you. What is friction and what are the important things you should know in friction? There are two things you should know in friction. Let's say we have rough surface and the mass capital M placed on this rough surface. Then its weight is capital Mg. Perpendicular reaction, which is perpendicular to the surface, is R. When I pull this weight to right hand side by applying the force capital F to oppose my force, to oppose this force, there will be a friction applied like this. It is always opposing this applied force. There are two cases in friction. One is limiting frictional force. Limiting frictional force. Second one is equilibrium state. Equilibrium state. An object can be in equilibrium in two ways. One is when the object is at rest. Object can be in equilibrium if it is at rest. Sometimes it can be in equilibrium when it is having a uniform velocity. Uniform or constant velocity. This is derived from Newton's first law. Objects at rest and moving under uniform velocity are considered to be in equilibrium state. If this is in equilibrium state, we can say applied force is equivalent to friction force. Applied force is equivalent to friction force. Frictional force is the product of mu r. What is this mu? Mu is the coefficient of friction. Coefficient of friction. Coefficient of friction is given in the question. It is depending on the nature of the surface or depending on the contact surfaces. This rough surface and this rough surface of the weight. Mu is depending on those two surfaces. The product of mu and perpendicular reaction is friction. If the mass is in equilibrium, we can say this friction less than or equal mu r. I repeat, if the mass is in equilibrium, our equation converts to an inequality. Frictional force is less than or equal mu r. This mu r product maximizes at limiting friction. friction is equivalent to mu r. That is the general case. But when the object is in equilibrium, sometimes object can be at rest. That can happen if my applied force is much lesser than this maximum friction. Therefore, it is always less than, or sometimes it can be equal to this mu r product. Under limiting friction, Fr is equivalent to the maximum friction, which is the product of mu r, because limiting friction is the maximum frictional value that a surface or a contact surface can take. Limiting friction is the maximum value of friction. In O levels, you had this graph from 0 to limiting friction. The value of friction increases with applied force. With this applied force, friction also increases linearly like this. After reaching limiting friction, it will drop to a certain value and again continue like this. This topmost point or maximum point is called limiting friction. There is no frictional value a certain surface can reach beyond limiting, that is the maximum. Therefore, if in the question they have given this is in limiting friction, you can equate the product of mu r to maximum friction. If the problem is telling about an equilibrium case, that means friction can be somewhere here below maximum friction. We don't know whether it has reached the maximum value or still it is in between this range. Therefore, we have to use this inequality. Sometimes it can be equal, but most cases it is less. Therefore, when the object is in equilibrium, you have to use inequality for the calculation. If it is in limiting friction, you have to use the equation. So keep those two things in mind. Okay, these red color things are enough. Even though I explained everything, to solve and take these inequalities, you should know only these two cases. Equilibrium, if it is equilibrium, inequality, if it is limiting friction case, equation. Okay, after this frictional theory discussion, we can start our problem. A rough mass capital M is connected with a smooth mass simple m using an elastic string of length simple a and modulus of elasticity m naught g. This is m naught g. The two masses were kept on a table such that the string is in its unfold state. The mass m is then projected along the table away from mass capital M with a velocity of u. So here we have two masses, capital M mass connected with an elastic string to another mass simple m. Both these masses are on a horizontal table. String length is A. Masses were kept on a table such that the string is in its unfold state. String is stretched to its natural length, not beyond its natural length. That is the meaning of unfold. The mass m, simple m, is then projected along the table away from capital M, that means to this direction, with a velocity u. If capital M is stationary, show that simple m performs simple harmonic motion. So first part is to show the motion performing after this projection is simple harmonic. Therefore, we have to consider a general point after the projection. It is projected with a velocity u. Then let's say this extension is x. Then here we have the opposing force, which is tension. Now we can apply F equals ma to this direction. X is measured to right. That is the reason. Opposing force minus T mx double dot. So tension for this elastic string is modulus of elasticity m naught g into extension is x over natural length, which is E. Now we can't cancel m because here we have m naught, not m. Then what is my x double dot? That is minus m naught g divided by ma into x. Is this our characteristic equation? Yes. The only difference is there is no bracket. Still, this is the characteristic equation of a simple harmonic motion. You have to write that statement. This is in the form of a characteristic equation of simple harmonic motion, where omega square, the constant, is m naught g over ma, and center, what is the center? How we can find center x? By equating the bracket you will get here to 0. Here this is just x. So when I equate that to 0, our center is when x is 0. So in order to find the center of this simple harmonic motion, we have to take this x to this point. So this is the center. Let's mark it as C. Now we have to apply second equation, velocity equation. By applying velocity equation, we can find the amplitude. I'm going to apply v square equal omega square times amplitude square minus x square. Where do we know the velocity? At center v, it is given in the problem. So this is applied at A. Velocity is u, its square is taken. Omega square is m naught g over ma into amplitude capital A. Now what is the separation between point A and center of our motion? There was no point A given, no? This is C. This is C, this point, not A. Separation from point C to center of our motion is 0. because point C and center coincide. Therefore, separation is 0. Then here we have m naught g a square over ma equal u square. Then what is the amplitude? Amplitude square is ma u square over m naught g. Then what is our amplitude? Amplitude is square root of this ma over m naught g square root into u. That is the amplitude. So let's mark our amplitude somewhere here. This is the amplitude point. Let me mark it as T. Then what is the separation? This is the value denoted by capital A. Okay. In the first case, we have to identify or obtain an inequality like this. Show that mu. What is mu? Mu is the coefficient of friction between capital M and surface, because this capital M mass is rough mass M. Then there should be the coefficient which I mentioned here, that is given in this problem as mu. Mu is greater than this value. And how to find that? That means we have to consider friction in this case. How to take friction to this particular problem? We can say mass M is stationary. Mass M is stationary at rest. If M is at rest, means it is in equilibrium. Can you see? If a mass is at rest or moving under uniform velocity, that mass is in equilibrium. Therefore, we can apply the inequality. If you consider as limiting friction, you can't obtain an inequality. It is an equation. So, M is at rest. Right hand forces equals to left hand forces. Here we have a tension. Here we have friction. Let me mark simple Fr. Then tension is equivalent to friction Fr, first equation. And here we have a perpendicular reaction applied from rough surface to M. Then R is capital Mg, second equation. And also we know tension is equivalent to modulus of elasticity into extension, which I can take as x over natural length A. And also, since M is in equilibrium, since M mass is in equilibrium, what is the theory? Friction Fr in this case is less than or equal mu r, product of coefficient of friction into perpendicular reaction. Then what is friction? That is tension less than or equal mu r. What is r? That is capital Mg. So I took friction as tension from equation 1 and r as capital Mg from equation 2. Then what is tension? M naught Gx over A, that is taken from third equation. mu mg. This is our third equation. Now, there is no equality given in this inequality. Only greater than symbol is there. Now we have to change this inequality sign to just less than, and also there is no x given here. Instead of x, we have to substitute u. So those are the finite things you should observe during your simplification. You have to convert this inequality to just less than symbol and also replace x with u. How to do that? What is this x? X is an unknown letter taken by me. That is this extension. That is the extension. This extension can go up to d because d is the amplitude. D is the amplitude. So this extension can go up to d and still mass m is stationary, because if m is stationary, simple m can perform a simple harmonic motion. In order to perform a simple harmonic motion by simple m, capital M must allow simple m to reach its amplitude. Otherwise, simple m can't perform a simple harmonic motion. In order to complete a simple harmonic motion, simple m must reach its amplitude. So, it is allowed by capital M. Therefore, the maximum extension where simple m can go is its amplitude. Now I can write that logic. M, capital M, is at rest till m reaches d, that is amplitude point. That means x, our extension, can go up to amplitude. What is amplitude? Ma over m naught g square root into u. This is very important. Therefore, I can replace this m naught g divided by simple a into x. X is this one, is less than mu mg. Because of the same reason, we can avoid the equal mark. If I want to put the equal mark, it should reach limiting friction until m is reaching d. This one O. Even though this m particle is reaching d, still this is stationary. That means m can go beyond d as well, but for simple harmonic motion, the maximum it can move is d, but still it can move beyond d if it is allowed by the simple harmonic motion. Therefore, it cannot be equal. It cannot be equal. It can go more than d as well. So that's why I didn't use equal mark there. Now I can simplify. G can be cancelled. To do that, we should know G is a positive answer. Yes, gravitational acceleration is positive. And what else I can simplify? I can write mu in left, mouth open to mu, then this is the correct direction of inequality sign. In this side we had m naught that got cancelled. This square root m naught get cancelled with 1 m naught in numerator. Then 1 square root a get cancelled with this square root a. Here we have square root a. Then here we have simple m, it is not cancelled. Then here we have capital M, it goes to denominator. All those things are in square root, inside square root. Sorry, not capital M. Capital M is not square root. Here we have a and square root g. Square root g is here. Then capital M goes to denominator and numerator we have u. This is the final answer. See carefully. M goes down and u over m. You have u over m. M naught ag. M naught ag. So this is the inequality that you must show. Then there's a small part. After finding this, you have to find the period of motion. For that, you can use period equation 2 pi over omega. That I'm not going to teach. This is the difficult part. So I taught you friction, and applying that friction theory, we could get this inequality.